Hi everyone. I am Apostolis Tsorvantzis, and I will talk about bandits with evolving states for online platforms. This is joint work with Khashayar, Khosravi, Renato, Paes, Leme, and Chara, Podimata. Let's think about interactions between users and online platforms and what happens during these interactions. Notice that this type of interactions can be expressed by this feedback loop, where the user consumes contents and ads, and online platforms recommend contents and ads. Online platforms want to predict the user's preferences, and to do this, they make recommendations by observing users' consumptions. So, in this feedback loop, the blue arrow is affected by the red arrow, but in reality, the red arrow is also affected by the blue arrow. This means that users' preferences are affected by what they have been exposed to. For example, assume that we have a user that at first wants to see some sports, but as the time goes by, they want to see some comedy. But as time goes by, they want to see some drama and action. So the corrected goal of online platforms now is that, again, they want to predict the user's preferences, but while they're shifting over time. The main questions that we're going to answer in this talk are first, how do you capture these shifting preferences? And second, given such shifting preferences, how does the platform learn to the best sequence of content and ads to suggest? Now, I'm going to highlight our main contributions at high level, but as the talk goes by, I will be more and more technical. Our first contribution is a new bandit model called Bandits with deterministically evolving states for the problem with shifting preferences. Then I'm going to give a variety of algorithms, and more specifically, I'm going to give learning algorithms for the platforms asymptotically close to optimal recommendation sequence. And also prove the robustness of our results to model specification. I know that this does not make any sense right now, but I will explain it later. So let's start from our model. And as a bandit model, it has arms. You can think arms as contents. And each arm is associated with a couple of unknown parameters, Ri and Bi. Ri is the expected reward sampled from this arm if there was no shifting preferences. This is something like μi in the stochastic multi-arm bandit model. And Bi is a new parameter that expresses the effect of the user's preferences after bringing this arm or content. Our model goal is to move from preferences to evolving preferences, and to do this, we introduce a notion of state. State expresses how users' preferences are lookalike at some round t, and also how the user's preferences are evolving over time. The definition of the state is by this equation. Recursive equation here with Qt. Okay, I can. Okay. With Qt, we symbolize the state, the value of the preference state at round t. With HT, we symbolize the history of the contents or arms that the user has been exposed to until round t. Lambda is a new parameter that is named evolution rate, and expresses how fast the user's preferences are evolving over time. And BIT is the value, is the BI of the arm that is pulled in round t. So if you can see, the recursion of this equation makes the state to be affected by all the BIs that the user has been exposed to. This equation also matches with the results of Holt et al. In 2015. Holt et al.'s work is experimental work where they chose a subset of users on YouTube, and they expose them in a mix of ads, and they measure how the preference of these users are affected. Sorry. Yeah.
A QT is a vector or
QT is a value.
Just think of that. So
Yeah,
there's an index missing in terms of I, is that right? Or
is the index?
well, you have many arms. So above you describe it in terms of RI, BI. So Q of T of +1 is referring to what?
It's very it has the history includes all the arms that have been played.
What is QT?
QT is the value of the state, the perfect state.
And
It's
how
value
does-
0, 1.
How does the state affect the rewards and the BIs?
Oh, we're gonna say it in a while. Okay.
If I can help, I think the preferences here are for the users.
Yeah.
You see the options, so there's just one user.
Yeah. It's one user, and the value of this state expresses how the preferences of the user look like. It's just a value 0, 1. And how the rewards are affected by this, we're gonna see it in a while. Okay. Yeah. So let's give some remarks. Lambda is the parameter for the shifting speed. As we said before, lambda belongs in 0, 1 as Ri, Bi's, and Qt. And as it gets bigger, the preferences are shifting faster. We can see by the factors of the previous history Qt of the recursion and from the last pull down Bit. We can see that 1 minus lambda goes to 0 if lambda goes to 1. And playing repeatedly 1 hour high for an infinity time makes the state convert to the BI of this arm. We can see the plot also. Here we have BI equal to 0.15, and we can see that as we play repeatedly 1 arm, the state converts to the 0 to the BI 0.15. So the BI is also the end state reward. Let's move now to the learning protocol. We have K arms, T rounds, and in each round T, the reward is summed from the Bernoulli of the product RIT times the product RIT QT. So the expected reward in each round is equal to the reward that we would take if there was no shifting preferences times a value that expresses how the preference of the user are looking like at this round. The goal now is to minimize the new notion of regret. That looks like a dynamic regret. Is a balance with the initially evolving state regret with respect to the optimal sequence. Here, if you look carefully at the benchmark, you can see that the cumulative reward that the algorithm collects is compared to the expected cumulative reward that the optimal sequence of arms by star collects. So the balance with the initially evolving state benchmark is harder than the external regret. And let's try run an instance of BDS with external regret minimization algorithms. Assume an instance where we have 2 arms. The BI of the first arm is equal to 0.9 and the RI equal to 0.1. And the other arm has BI equal to 0.3 and RI equal to 0.8. And if we try to run XP3 UCB and active elimination, we have linear regret. This is because this algorithm converts to a fixed optimal action, and the optimal sequence here by star consists of both of arms.
Sorry, just to make sure that I understand correctly. Your QT is a single number that is jointly determined by all of the bandits, right?
Yeah.
So it's a particular model of how preferences evolve, in the sense that I could have imagined that my appreciation of alternative I is just determined how often I have used, say, alternative I. But
Yes.
Here, the use of alternative J is in fact determined by some experience I had with alternative I before. Right? I mean, just from the way you described the model.
Yes.
So I'm just, I guess I'm naturally curious To what extent your result depend on that particular configuration of preference in which basically the experience of the queue is conflated over all of the bandits rather than say separately and independently, which is
Yeah. If I decide, you say that all the rewards of all arms
yes,
are decreasing uniformly.
exactly.
Yeah, yes, that's true, and that's why here the QT expresses how the user likes is happy with the and if you do it in multi-dimensional, then you get this one, the full parentheses, and there's a here that we're working now. Very good question.
Great questions. Just in the interest of time, let's take the rest of the questions at the end because we have very few minutes.
So let's move now to our algorithms for this model, and we have different algorithms for different values of lambda. At first, we assume that lambda is known, and we start with lambda near 0, and this case is named slow evolution rate, and we get the square root of KT regret. Then we move on for lambda in this blue interval, and this is the general lambda. And then we move to the fast evolution rate, where lambda is near 1, and we get k times square root of t regret. Let's start with the slow evolution rate here, and for lambda equal to 0. Here, if you remember the equation, there are no shifting preferences, and as the user consumes some contents, the contents are not affect the user's preferences. So if you take a look at the rewards right now, they are drawn from Bernoulli IT, and this is a stochastic multi-arm bandit model. So we can run UCB and take square root of KT and we're done. But if the lambda is near lambda, there are changes, but they are so small that they not affect the regret. And we get an additional 1 minus lambda in t times salt, which is sublinear for lambda in this interval. So let's move to the general lambda and our main algorithm. The first step is to solve the offline version, and assume that someone reveals the rising BIs. To solve this problem is NP hard. So we give an NP task dynamic programming algorithm that looks like NAS. Next, we have to define how do we learn RIs and BIs. The problem here is that it is very difficult to disentangle the RIs and BIs if you just play random Tsorvantzis. So we do a trick here that I will explain with an example. Assume that in round tough, your state is at values 0.6, and if we play in the next round an arm with BI equal to 0.15 and lambda equal to 0.5, the value of the state becomes lower than 0.4, and if we play it again, it goes below the 0.3, and if we play it again, it becomes near 0.2, and if we play it for near lambda rounds, the state becomes epsilon near BI. So now think that if you play repeatedly near lambda rounds one arm and bring the state near BI, then the next step, if you play another arm, then you can observe a value, take a sample from a value that is near to RIJ or RJ by I. Okay. So now, if we do it again and again and take samples and make estimates about this product, about some of these products, we can disentangle RIs and BIs in the learner. If we mix all these ideas, we can construct an algorithm, explore the commit algorithm, where we learn first the RIs and BIs, And then for the rest of the rounds, we call the offline algorithm to take the near optimal sequence for the rest of the rounds. And we play it, and then we get a k times t lambda in 1/3 times t in 2/3. Good. So now let's move on to the fast evolution rate here and start with lambda equal to 1. Here, in each round t, the state becomes equal to the b of the previous pulled arm. And because of this, the optimal sequence pi star is either just playing alternatively 2 arms I star and J star, or just playing repeatedly 1 arm I star. So the optimal sequence pi star is like I star, J star, I star, J star, or I star, I star, I star, I star. And the reward, the expected reward every 2 rounds is equal to Ri star times Bj star plus Rj star times Bi star. Here, I star and J star may be equal for the case of repetition of 1 arm. So we have k square candidate pair of arm sides A and I, which we call meta arms. And someone would say that, okay, you can run UCB on these meta arms and get k times square root of t regret. But that's not true. It doesn't work. And I'll explain why, the reason why, with an example. Assume that we have 2 meta arms, Ij and KL. And at some round T, you want to switch from one meta arm to the other. And the problem here is that the state, after you take a sample from meta arm Ij, is equal to Bj. And to sample KL, you want your state to be equal to BL. So to bring the state to the correct value, you have to play RL times Bj. And this may lead to linear regret in most cases. How do we fix that? We will need to minimize the switches. And we do it in 2 steps. The first step, we use the Bandits UCB algorithm, which is introduced by Khashayar et al. In 2020. And this algorithm, we explore in log T phases. And in each phase, we play every active arm in Bandits in multiple times. Here in the first phase, we played it W times. So we play Ij at arm W times, and then we move to another at arm. And if you see in the phase Vita, we played it for W and Vita. This is the W Vita times. The size of the buds is increasing exponentially. And also we had the second step, we changed the switching policy. Here, the policy is like every time you pay a switching cost for 1 arm I, then you play all the meta arms that include this meta arm. So from k square switches per exponential phase, we reduce to k switches per exponential phase. So now, if you put this together, we can get the results that we would get if from UCB there was no switching costs. For lambda near 1, again we play, we pretend like lambda is equal to 1, and we get an additional 1 minus lambda times soft regret, which is lower than square root of t for lambda in this interval. So already have present the first 2 contributions, and the problem here was that okay, we have an assumption for lambda that it is known, and we overcome this assumption by giving an algorithm that learns lambda. We also prove some lower bounds for lambda near 0 and 1. And about the robustness that I said before, we just add randomness in the evolution the evolution equation of the state, and by adding a sub-Gaussian noise zeta, and we prove that our algorithms are robust, and they get additional sigma times d regret, where sigma is the variance of theta. Thank you for your attention.